So let's talk about the energy of light. The unit that we're going to use to measure energy is the joule. All right. Named after the English physicist James Prescott Joule. You guys used that unit of energy before? Familiar with joule at all? Yeah. I wasn't sure if you talked about that in physical science, if you'd used it before, but anyway, that's going to be the unit that we use. Just to give you some frame of reference, a joule is roughly 1 joule is roughly the energy. I'm supposed to say that the energy to lift a small apple. So roughly how much energy it takes to lift up a small apple. 1 meter, sorry. That's all I need to tell you the distance. Because the higher you lift it, the more energy it takes. 1 meter, all right? Again, just a frame of reference. I'm not really going to test you on that, but that's what a joule is. James Prescott Joule. I have to do something about that. My big feet. There's not anything you can do about the big feet, so I just make more room. Here's kind of an interesting quote. I like this quote from Joule. He said, "After the knowledge of and obedience to the will of God, the next aim must be to know something of His wisdom, power, and goodness as evidenced by His handiwork." So now I've told you guys this before. So many of these scientists in the past, they were driven by this desire to understand more about God. They recognized that this world was created by Him, and so I'm studying the things that He made, and so in doing that, it's a pursuit of learning more about Him. And so Joule was one of those that was driven by that passion and that desire. And so I always like to share that whenever we know that about the individual. But anyway, I want to give you an equation for energy. And let's see, the E, of course, is for energy. The F is for frequency. So it's E equals HF. You got to make sure that you know that. And the H here is what we call Planck's constant. And when we say constant, what do we mean by that? It doesn't change, right? It's going to be the same. We learned a constant last time when we were looking at the equation for wavelength. What was the constant that we learned last time? The speed of light, right? So the speed of light, we said, is a constant represented by a lowercase c and equals 3 times 10 to the 8 meters per second, right? So Planck's constant is, again, you got to get that scientific notation down on your calculator. So make sure that you've got that, you figured that out. How your particular calculator works. It is 6.63 times 10 to the negative 34 joule seconds. So that's the unit for Planck's constant. It's got the unit for energy and the unit for time in it. 6.63 times 10 to the negative 34 joule seconds. No need to memorize. All right, if you need that on a test, I'll give it to you. All right, so notice here, one of the things that we said about wavelength and frequency was that they were inversely proportional to one another. You guys remember that when we looked at the equation for wavelength? And so what does that mean when it's inversely proportional?
When one number gets bigger, the other one gets smaller.
Exactly. Yep. So as one goes up, the other one goes down, or vice versa, right? Now, so that's the way wavelength and frequency are related to one another. And you remember we said you're standing in the ocean, the waves coming in. The longer the wave is, the less frequent the waves are hitting you, right? So that makes sense that when wavelength is bigger, that frequency is shorter, right? Well, here, you notice with energy, though, frequency and energy are what we say they're directly proportional to one another, right? So as one gets bigger, so does the other one. Since H is a constant, since that doesn't change, then if frequency goes up, if it gets larger, then energy is going to be larger as well. And when we talked last week about the electromagnetic spectrum, and we talked about the light that was outside the visible spectrum, right? We said there were dangerous versions of that, right? There were things that we're not concerned about, like radio waves and microwaves. There were things at that end of the spectrum that don't kill human tissue, but we said the other end of the spectrum we have stuff that does, like ultraviolet light, X-rays, things like that. And what we noted with those is that the frequency was higher in those. And we said that sort of makes sense, right? Because if the frequency's higher, that wave is hitting you a lot quicker. Well, if the frequency's higher, also the energy that's coming against that tissue is higher as well. So that sort of makes sense that it would be the higher the frequency, the more dangerous it is to us, right? Because more energy is produced by that. So let's do an example on page 82, just to work with this equation. Really simple example. If I'm testing you on this equation, not a whole lot I can do, except we've got two equations now, right? We've got an equation where we can calculate frequency or calculate wavelength if we have one or the other. And now we've got frequency related to energy. So you can imagine then that I might give you a question that says, here's a particular wavelength. If I give you the wavelength, you can find the frequency. And then from that, you can plug it in this equation and you can find the energy, right? So that's exactly what this problem is doing. They give us a wavelength. It's the shortest wavelength of visible light, they say, is about 380 nanometers. Remember, wavelength, we use the Greek letter lambda to represent wavelength. And so they give us the wavelength and they want to know what is the energy of this light, right? And so we have all the information that we need because we're going to need a couple of constants to calculate that. We need Planck's constant, we need the speed of light constant. So the first thing that we're going to have to do is we're going to have to use our equation lambda equals c over F. From that we can calculate F, and then we can calculate energy from that. But before we can start plugging numbers in here, what do we need to do first? Yes?
We need to find the frequency.
We need to find the frequency, that's correct. So we need to rearrange this equation so that we're solving for frequency, right? I'm still seeing some people miss that. Just this kind of simple rearranging of algebraic equations, you got to get that down, right? And so I'm going to go through it. Yes?
Don't we also have to change the unit?
We have to do that as well. Yeah, that was the next thing I was going to ask you about. So good. So we do need to rearrange this. So we'll go ahead and do it since we mentioned that first. And just to walk through that one more time. All right, last time. If I want to solve for frequency, I'm going to multiply both sides by F. Right, my F's will cancel out here. So on this side I got frequency times wavelength equals C. Then I divide both sides by wavelength. The wavelengths will cancel out there. So F equals C over wavelength, right? So that would be how I would rearrange that equation. And notice, even when I rearrange it, F and lambda are still inversely proportional, right? No matter how you rearrange the equation, you know that they're still going to be inversely proportional to one another. So if you were to rearrange this equation and all of a sudden they're directly proportional like these are, then you know that you did something wrong, right? All right, but you're right, because the units for this are meters per second, and the units for the wavelength here are nanometers. Before we start plugging in this equation, F equals C over lambda, we need to make sure our units match. And so typically when you're converting one, you want to convert it to the base unit. So in this case, meters is our base unit. So let's take this guy and convert it from nanometers to meters. And so in order to do that, we have to remember that last week we said 1 nanometer is equal to, does anybody remember? How many meters? Huh? 1 billionth of a meter? What did you say? 10 to the negative 9. Yeah, so it would be a billionth, right? But 1 times that equals, I write it down like this just because that's how we have to punch it in the calculator, right? Or it's easier if we use our exponent key. But 10 to the negative 9, or 1 times 10 to the negative 9 meters is equal to 1 nanometer. So first, let's do that conversion. So 380 nanometers. What are we going to put on the top, meters or nanometers? Meters. I had somebody miss that too. So don't forget, the unit you want to end up with is the one that goes on top. the unit that you want to cancel out is what's going to go on bottom, right? So that way our nanometers cancel out. And so we're left with 3.8 times 10 to the negative 7 meters. That is our wavelength in meters. Now we can plug in this equation, right? So we'll do that over here. Here F equals c over lambda. C, the speed of light, is 3 times 10 to the 8th meters per second. Lambda, we calculated to be 3.8 times 10 to the negative 7 meters. And so when we punch that in our calculator, we get 7.9 times 10 to the 14. And what's our unit for that? Yep.
Technically hertz.
Hertz, yep, which is also equal to a per second, we said last time, right? So since in this case we're just gonna, we want our seconds to cancel out in the next equation, we're just gonna leave it like that instead of writing it as hertz. Yes?
Shouldn't the 7.9 times 10 to the 14 be?
Wait a minute, I'm sorry, yeah. Good catch. I'm gonna give you an extra one for correcting the teacher. Nice job, thank you. All right, so per second, 7.9 times 10 to the 14th per seconds. Again, just to make sure that you understand why this works out like that, meters per second over meters is the same as this times the reciprocal of this bottom equation. That's the same as m over 1. So m divided by s times the reciprocal, which is 1 over m. Your m's cancel out and you're left with 1 over s, right? So that's how those units work out. Again, these are kind of simple algebra things, but you got to make sure that you remember that stuff if you're going to get the correct answer. All right, so we've figured out frequency. Now we've got to plug it in our energy equation, right? So our last equation was E equals HF. So we've got Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds times. Now you see why joule seconds works out, because we're multiplying it times 7.9 times 10 to the 14th per second. So our s's are going to cancel out here, and we're left with a unit of joule, which we said is our energy unit. And so punch that in, 5.2 times 10 to the negative 19th power joules. All right. Any questions about that? Everybody follow those steps? So, if I want to give you a problem where you use both of these equations, maybe I could go in the opposite direction, right? Maybe I could say we have light that we know, produces a certain amount of energy. And so can you tell me what the wavelength of that light is in nanometers? So it'd be all the stuff that we just did, but in the reverse, right? You rearrange this equation to solve for frequency. Then you take the frequency and you plug it in this equation here to get the wavelength. And it'll give you the wavelength in meters, and then you'll have to convert the meters to nanometers. So you could go in the opposite direction that way. So these tricky teachers, we do stuff like that. So you gotta look out for things like that. Any other questions? All right, let's move on to our next topic, which is the Bohr model. The Bohr model of an atom. So I'm pretty sure a kid fell asleep in my last class. No, it wasn't Joshy. No, I would have thrown something at Joshy. But, so he probably would have written that like that, right? The Bohr model. That was a good one, Mr. Walker. He really did fall asleep, I'm pretty sure. But no, this is exciting stuff, right? We wouldn't write it that way. This is the Bohr model, named after Niels Bohr. He was a student of Rutherford. Remember, Rutherford is who we credit with what?
The planetary
Planetary model of an atom, right? So he was working for a guy that was already doing, work on trying to figure out how atoms were constructed, and so he came up with this idea that there's a nucleus, and the electrons orbit around this nucleus. Well, Bohr did some work. He was a Danish physicist that came up with some ideas as far as how what those orbits are actually shaped like. Wasn't exactly like we see it today, but still he made some pretty significant advancements. And one of the things that kind of came out of Bohr's work had to do with wavelengths of light that are emitted from atoms of a particular element. Okay, so let me just say, so what scientists discover is that if you add energy to elements in the form of heat, for example, that if you add energy to the elements, that those elements will emit certain wavelengths of light. And you can actually tell which element is by which wavelength of light it emits. And so with wavelengths of light, what did we say the wavelength determines as far as the light's concerned? You guys remember that from last lecture?
The wavelength determines the color.
The wavelength determines the color of the light, right? See, Joey wasn't even here and she got that right. Amazing. But the wavelength determines the color, okay? And so, let me just write these down. I want to make sure that you know this, that these wavelengths emitted by an excited atom, and that's an atom that's been like heated, energy's been added to it, right? So it's excited, and excited atom are called its atomic spectrum, right? And you can see, no, we're not going to get to that yet. We're going to see an example of that in just a moment. I'll show you in the book. But first we want to talk about Bohr before we get there. So Bohr began doing some work trying to figure out why this is the case, right? Why is it that we can see that elements, depending on the element, they have a unique atomic spectrum, certain wavelengths of light that they emit whenever we add energy to it. And so his work led to what we refer to as the Bohr model of the atom. And the Bohr model said electrons had specific circular orbits around the nucleus which were concentric circles. In other words, circles within circles. So he came up with this idea to explain these unique wavelengths of light that were emitted. And he said, okay, here's the way that it works. There are circular orbits around the nucleus. And so let's take hydrogen, for instance. Hydrogen's got a single proton in its nucleus. No neutron, just a single proton. And there are orbits around that nucleus that the electron orbits the nucleus in, okay? And so what he said was happening, we refer to this first orbit here as n equals 1, that's the lowest energy state. This would be n equals 2 right here. This would be n equals 3. All right, and he said that normally electron is going to want to orbit in the lowest energy state. In other words, the n equals 1 state, right? So it wants to stay here. This is the easiest place to be, right? The path of least resistance. And so it would just kind of hang out here until some energy was added in here, until the electron was excited. When that happened, the electron would jump to these other orbits, right? So it may get enough energy to jump there, or it may get enough energy to go from here all the way out to there, right? Or, there are additional orbits around this. And so he said, as it jumps to these orbits, it's out there because energy was added, it got excited, but it wants to be at this lowest state. So what happens is after a time, if it's, say, circling out here, orbiting the nucleus in the n equals 3 orbit, after time it begins to give off energy in the form of light so that it can jump back down here to the n equals 1 orbit. And so when it gives off that energy, it produces a specific wavelength of light, and so that's why it was unique to each element, because these orbits were unique to each element. That was what he theorized. And so he said, and so basically what came out of this is he did a bunch of equations with the hydrogen atom and how these wavelengths work and all, and I mean it fits it really, really well. He was spot on with the hydrogen atom. What we don't agree with now is this idea here, that it's circular orbits. All right, we do agree that there are, with the atoms, that there are different orbits that the electrons take around the atom, but well, first of all, we don't live in a two-dimensional world, right? We live in a three-dimensional world. So it's this first orbit here isn't really a circle, it's actually a sphere. The electron can be anywhere inside that sphere as it's orbiting around it. But they get even more complicated as you move out further away from the nucleus, and we're going to study that in greater detail later on. But still, like I said, his idea of the model of the atom actually explained it very well for hydrogen. He did a lot of work with hydrogen, and it helped us come to that understanding that what's happening when this light is produced is that the electrons are jumping between these orbits. And so the cool thing about that is that because of that, we can look at the wavelengths that are emitted from an atom, and we can determine what element it belongs to, because it'll be unique for that particular element. Let me define something called ground state. And ground state is the lowest energy state of a particle. Yes, you can. You don't want to walk in front of the camera? All right.
I'll give it to Josh.
Okay. See ya. All right. So the lowest energy state of a particle is the ground state, and so for the case of the hydrogen atom, this is a hydrogen atom, and this would be the ground state for its electron, n equals 1. That energy state. So Bohr said that the reason these wavelengths of light emitted by each element were unique was because there were specific energies that were required to go to each of these orbits, right? And so if, like I said, for example, if it got excited enough that it went all the way out here to this energy state, then when it dropped down from the n equals 3 orbit back to the n equals 1 orbit, it would emit a specific wavelength of light. If it only got enough energy to jump out to the n equals 1, then when it would drop back down, it would emit a different wavelength of light. And so sometimes it might get bumped all the way out here to n equals 3, and when it gives off energy in the form of light, it might go directly back down to n equals 1. Or sometimes it might be out here and it go first to the n equals 2 orbit, and then from there it drop back down here. And so it would emit light to go from energy level 3 to 2, and then emit another wavelength of light to go from energy level 2 to 1, right? So there were all these different wavelengths of light that would be emitted as that electron was jumping around. And so if you look on page 84, you can see that atomic spectrum that we were talking about for they've got 6 different elements here that you can see the atomic spectrum for. So like I said, even though Bohr's model is not entirely correct, and we'll find out more about that later on in the class, his model was very accurate for the hydrogen atom, and it did help explain to us why electrons had to emit specific wavelengths of light in order to return to their ground state. It's because it takes a specific amount of energy to go from here to here, and from here to here, or from here all the way to here, depending on which atom it was. These orbitals, the energy state of these orbits varied. And so that was a groundbreaking discovery there, to be able to prove that. And so we've got these atomic spectrums now. You'll see, like in the case of lithium on page 84, there are only two wavelengths there on that atomic spectrum. Sodium and potassium both only have one wavelength of light. But that really doesn't make sense to us. If there's all these different energy states, why would there only be one wavelength of light, or only two wavelengths of light? We would expect to see a lot more, right? We would expect to see something like what we see in calcium or strontium or barium. Any ideas? The reason we only see one is because the wavelength of light that's emitted as it's jumping from those other energy states, is not in the visible spectrum, right? Remember, we talked about X-rays, and we talked about microwaves, and all of these energy states all of these wavelengths of light that were outside the visible spectrum. So they're actually more light is produced for lithium and sodium and potassium than what's listed there, but that's the only visible light that's evident. So that's why it shows up in its atomic spectrum. Questions about that? Does that make sense? Kind of, sort of? Something else that kind of came out of this discovery was that, like I said, Bohr does all this work with the hydrogen atom, and we understand now that that atoms are mostly made up of space. And so, if you just kind of as a frame of reference, if you had a football stadium, right? Let me draw a little football stadium here. What we're going to do? I didn't do it quite right? You got this big stadium around here, and I mean nowadays, right? The stadium runs all the way around out here and all. Well, if right here on the 50-yard line in the middle of this stadium, we had the nucleus of the hydrogen atom represented by a marble sitting there on the 50-yard line, the electron would basically be orbiting on the outer rim of the upper bleachers in the stadium, right? So that's how much empty space is in there. And remember, we told you protons are much larger than electrons are. So I mean, if it's marble size, electron 1,800 times smaller than that. So almost, mostly just empty space, almost just empty. Pretty amazing. That's the building blocks of everything, right? The reason that this table doesn't give way is there's all those atoms in there, right, that are tightly joined together and give it that solid structure so it doesn't fall apart whenever I press on it. But anyway, our experiment that we were planning to do today, and Lord willing we'll do next week, had to do with this idea that you can identify an element by its atomic spectrum. And so if it's emitting a particular wavelength of light, when you add energy to it in the form of heat, you should be able to figure out by those wavelengths of light emitted what element it is. And so you ladies already have a jump on that, right? Because your mom's well educated you. When you see a particular color firework, it's like, okay, what elements are in that firework based on the color? I think it's pretty cool, but if I grew up being hammered into me every July 4th, maybe not, right? Okay, so let's talk about, just real quick, make a note about spectroscopy. And spectroscopy, make sure you understand what that is. This is the process of identifying chemicals by studying the light they emit, or absorb. So either way, this spectrum that we're looking at here, right here, for lithium and sodium and potassium and so forth on page 84 in the book, you can determine that spectrum either by understanding which light a chemical emits, like what we're going to do in class, or which light it absorbs. So if you have a piece of if you have something that's full of particular elements that's transparent and you shine light into that, white light's got all of that, the full visible spectrum in it, and you shine that light in there, then what comes out on the other side? You can look at the light that passes through, and if you consider the light that didn't pass through, the wavelengths that didn't pass through, then you'll get this atomic spectrum right here. So that's where it absorbed certain light, right? The light it absorbs or the light it emits can tell us the atomic spectrum and help us to identify which element they belong to. And so, for example, sunlight. When sunlight reaches us, we can look at the atomic spectrum of sunlight, and we can see which wavelengths are missing from the sunlight that's coming to us, and the ones that are missing correspond. That helps us understand which elements are in the sun. So scientists can actually determine what stars are comprised of, what element stars are comprised of, by looking at the light that's emitted from that star and figuring out its atomic spectrum based on that. So that's pretty cool, huh? I mean, who would have thought, just from the work that Bohr was doing all those years ago, that we could be able to tell what a star was constructed of? I mean, that I find that amazing, So pretty fascinating things kind of came from these discoveries. But here's something even more fascinating. All right, you ready for this? Get ready for your mind to be blown, right? Psalm 147 verse 4 says, "He, that is God, counts the numbers of the stars. He calls them all by name." So they've done studies and they can tell us what stars are comprised of. God says, I can also tell you how many there are. And by the way, I've named each one. Right? So now that's mind-blowing. Right? So amazing discoveries. God's given men incredible light to be able to figure out things that I'm sure, a few hundred years ago, they never would have thought we could have been able to tell you what elements were in stars. But now we can understand that based on this study. But God says, yeah, I put them all there. I know exactly how many there are. By the way, he knows the numbers of hairs in your head, he says. Given the amount of hair that my wife loses on the bathroom floor, that amazes me, I don't even know how she has any hair. But pretty cool. So any questions about spectroscopy, atomic spectrum, using the energy equation, anything? No? All right, that's it, guys. I'm done.